Hello, physics students. It's Mr. Kennedy here. I hope everybody's doing well. I want to give you a little bit of a breakdown on our next lesson here, and that's going to be about conservation of momentum. So let's do a quick review, and we'll just see some of the things we've already learned. The first thing we learned was that momentum was mass times velocity, and we said that was really a measure of how difficult it is to stop something. Then the next thing we looked at was what happens when you change momentum. What happens when something comes along and changes it? When we have that, to change momentum, you have to exert a force over a time, and that is the change in momentum. Remember that both sides of this are really change momentum. This is impulse, this is change momentum, but they're really the same thing. And one of the things we want to be really careful about was the signs. Because this is a vector, you really have to watch your signs. Make sure that things that point one way are given one sign, things that point the other way are given another sign. Usually I call right positive and left negative, but if you flip it, it's okay as long as you are consistent. That's what really matters. But something comes out of this that might be a little bit surprising. If two objects interact and they push on each other, so let's say we have one object here and another object here, and they come in and they interact and they hit each other, then because the force is the same and the time is the same, then the change of momentum is the same for each one except equal and opposite. So what one gains in momentum, the other will lose in momentum, which means for the whole system, for everything in this little system here, the momentum has to be the same before and after any kind of collision or explosion or anything. And it turns out this is one of the most fundamental rules of our universe, that momentum in a system has to be conserved. Now, if something from outside the system acts on it, that's where you have this definition, that you have impulse. But if you have a system, then the momentum in the beginning must equal the momentum at the end. It's really similar to energy in that way, that the momentum you have in the beginning has to equal the momentum you have at the end. And we write this in two ways. One's a really simple way, and then one's a more practical way. Momentum in the beginning must equal momentum at the end. That is sort of the common conservation of momentum. Much like conservation of energy, that's conservation of momentum. But the way I like to write it is this. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And all this means, this stuff right here is before the collision happens, or before the explosion, or whatever else it's going to be. And then here, this is after the collision or explosion, or whatever else it's going to be. And I'm going to take a few examples here to give you an idea of what's going to happen. There is one additional thing we have to look for, though. And the extra thing we have to look at is something dealing with energy, kinetic energy specifically. Whether this collision is elastic, inelastic, or an explosion. So we're really going to be using conservation of momentum in all of these examples. We use this in all of them. But then we have to look at one extra thing, and it's whether these are going to be elastic, inelastic, or an explosion. So let's see. The consideration we have for that final piece is this. If it's elastic, we think of it as bouncing, but it's not really going to be bouncy balls that actually make it work. It's more like things like protons interacting with each other, or it's really heavy steel or pool balls or things like that. But if that's the case, then the kinetic energy in the beginning must equal the kinetic energy at the end, if it's elastic. Inelastic, which is by far the most common type of a collision you'll start with, or you'll deal with, the kinetic energy in the beginning is greater than the kinetic energy at the end. We lost energy. So here, things are equal. Here we lost some energy, and you lost it out to the environment. The environment is heated up in some way, and we've lost it. It's just not mechanical energy you're going to have back. And then you have an explosion. That's my third kind. The kinetic energy at the beginning is less than the kinetic energy at the end. In other words, something explodes, and we see a gain in kinetic energy that we didn't have before. And that came because there was some kind of energy stored somewhere that got released. So this is our last consideration when you're dealing with this. And really, this little video, once we're done, is going to mark out the last thing you really need to learn in momentum. First part was about impulse. The second part is about conservation momentum. So let's take a look at a really simple set of problems. We'll take a look at 3 problems, one of each of these, and we'll see how it works. So in the first one, let's say we have a little truck here. Little truck, and it's 2,000 kilograms in mass, and it's moving at 30 meters per second. And there's another car here, little car. This little car is 1,000 kilograms, and it's just sitting there at rest. So the velocity here is 0 meters per second. And what's going to happen is this truck is going to hit the back of this car, and they are going to stick together. They're going to stick together. I'm going to say that in the problem, and I'm going to say that right now, that they stick together and then they move off together. You know, it's like a rear end collision, and they get stuck together. The question is, how fast do they move together? And actually, this is how police use to figure out how fast somebody was moving before a collision. They use these exact same equations. So first thing I want to do, though, even though it's not as necessary for this problem, is I want to stress that I am calling everything that points to the right positive, everything that points to the left negative. There's nothing that's going to point to the left, but I want to be clear about that for all of these little, problems here. So let's start with conservation momentum. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And let's just plug in what we know, and then the answer will come out of how fast they'll move together. So I have 2,000 kilograms moving at 30 meters per second plus 1,000 kilograms moving at 0 meters per second. So that's my first part. This is before this collided. Equals, afterwards, I'm going to say that I have 2,000 kilograms, but I don't know how fast it's moving afterwards, so I'll just call it V. Plus 1,000 kilograms. I also don't know how fast it's moving, but I do know it's the same speed as here. I do know that they're stuck together, so they have to have the same speed. So it's 2,000 times 30 plus 1,000 times 0 equals 2,000 times some unknown speed plus 2,000 times some, or 1,000 times some unknown speed. So what I see on this side is 2,000 times 30, that's 60,000. And it's going to be, when I put these two together, that'll be 3,000 V. So I'm going to drop off my units just temporarily, and I'm going to say that I have 60,000 equals 3,000 V. So V must be 20 meters per second. And it's slower because the mass got bigger. It became a bigger mass when it combined together. So the speed is slower. So we started with an object moving at 2,000 kilograms at 30 meters per second. Now together they are 3,000, so now it's moving at 20 meters per second. So that's the momentum part. We know how fast they're moving afterwards. But now let's take a look. Was this elastic, inelastic, or an explosion? And we'll see what we have. So I'm going to do this, in a sense, longhand here. I'm going to do all of the pieces that need to go in here, even if it doesn't really make sense of what they, if they contributed. So the kinetic energy beforehand was 1/2 2,000 kilograms, and it was moving at 30 meters per second, plus 1/2 1,000 kilograms. I realize this is a little silly, but I'm going to put 0 meters per second. Oh, forgot to square those guys. And what I see is that I've got, this is 0. This doesn't contribute anything. But 1/2 times 2,000 is 1,000, and 30 squared is 900. So that means this total, whole thing, is 900,000 joules. That's how much energy I had before. Now, I go through again, I see what happens at the end. Kinetic energy final Well, now it's one object. These two, the car and the truck are really just considered to be one object. So this is 3,000 kilograms because they're just stuck together. You could add them together if you wanted to. When we get 20 meters per second squared, well, that's 1,500, and this will be 400. So doing that, I should get 600,000 joules. So when I see this, the energy that I had in the beginning and the energy I had at the end are not the same. I've lost some energy. I lost 300,000 joules in the collision. So this collision must be inelastic. And most collisions you'll have will be inelastic. Like in your everyday life, things collide inelastically. So that's one example of one of these problems. Let's take a look at another one. So in this one, you can think of these as like pool balls or glass balls or steel balls or something like that. But I'm going to have, right up here, I'm going to have a 1 kilogram ball moving at 2 meters per second. And then I'm going to have over here a 2 kilogram ball moving at 1 meter per second. And they're going to collide, and they're going to hit, and they're going to bounce off each other. And when they bounce off each other, this object here is going to move backwards at 2 meters per second. The question is, what does this one do? What is what's the final speed of this one? And then, was it inelastic, elastic, an explosion, etc.? So we just have to be organized. One thing I will say is that make sure to put in which side is positive and which side is negative. So everything that goes to the right is going to be positive, everything that goes to the left is negative. So m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. So m1 is 1 kilogram moving at 2 meters per second. That's positive because it's going to the right, plus 2 kilograms. This is moving to the left, so that's going to be negative 1 meters per second. And that's one of the biggest mistakes that students make, is they forget to label positive and negative here. And then here I've got 1 kilogram that's going to be moving at negative 2 meters per second, because it's moving to the left, plus, in this case, 2 kilograms at some velocity that I don't know. Again, if you just stay organized with this, you'll be fine. Now looking at some of the pieces here, this is 1 kilogram times 2, so that's 2, minus 2, so that's 0. And I'm going to drop the units out here for just a second. 0 equals, this is negative 2 plus 2v. Bring it to the other side, and I get 2 equals 2v, or the velocity is 1 meter per second. So that means this, the answer to this, how fast this is moving after the collision, is 1 meter per second. I knew that all the momentum before and all the momentum afterwards, so it all works out. Now let's see, is this going to be inelastic, or an explosion? And one quick thing, it has no chance of being elastic if it doesn't bounce off like it just did here. There's no way it can be elastic. Even when things bounce, it doesn't mean they're elastic. You have to check it anyway. But let's see what we have here. Let's see what we have. If we check it, the kinetic energy in the beginning is 1/2. And you don't have to worry so much about the signs with this one. 1 kilogram times 2 meters per second squared plus 1/2 2 kilograms times negative 1 meter per second. The reason you don't have to worry about the signs so much is because they get squared when they're in here. So what we see here, this is 1/2 times 1 times 4. So 1/2 of 4 is going to be 2 joules. This is going to be 1 joule. So I see I have 3 joules in the beginning. My kinetic energy afterwards, 1/2, 1 kilogram times negative 2 meters per second squared plus 1/2, 2 kilograms, times 1 meter per second squared. And you can see that this is going to be the same because it doesn't change much. The 2 was just negative, so now it's squared. And I have 2 joules here. And then here I've still got 1 joule. And it's still 3 joules. So this is an elastic collision. They bounced, and they bounced perfectly because the kinetic energy was the same. So in the first example, we lost energy, so that was going to be inelastic. In the second example here, we had the same energy before and afterwards, so we have an elastic collision. So let's take a look at one more. And in this last one, here's a little lab cart. So think of our little carts that we have in the lab. And here's another one right next to it. And this one is 1 kilogram. And this one is 3 kilograms. I loaded this one up. And I put a little spring in between them. So what I'm doing is I push them together, and I'm holding them together with this spring in between them, and then I let them go. And when I let them go, they're going to fly apart from each other. And when they fly apart, what I see is that the one on the left moves over at 3 meters per second. And the question is, what does the one on the right do? What does that one do? And then was this inelastic, elastic, or an explosion? Well, let's examine the whole thing. Conservation momentum is how you start. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. So, this might be silly to put it all in here, but this was being held together by me beforehand, so it wasn't moving. So this is 1 kilogram times 0 meters per second plus 3 kilograms times 0 meters per second equals, I'm going to say that I have 1 kilogram moving at negative 3 meters per second because I'm calling left negative. I'm going to say that that's my negative direction, that'll be my positive direction, plus 3 kilograms times some velocity that I don't know. Well, when I look at this then, this is 0, this is 0, this is negative 3 plus 3v. 0 equals negative 3 plus 3v. 3 equals 3v. The velocity has to be 1 meter per second. So I get 1 meter per second out of this. I know that the other cart can move at 1 meter per second. Let's see what kind of collision it actually was. Was it elastic, inelastic, or an explosion? So first we always do conservation momentum, then we do the energies. So when I look at the energy, the kinetic energy initially is 1/2, 1 kilogram, times 0 meters per second squared. I realize that's kind of silly to put that in, but I'm going to put it in. And then this was also 0 meters per second. They were just sitting there at rest. It has no energy. It has no kinetic energy beforehand. But then, afterwards, now it's 1/2. The 1 kilogram was moving at negative 3 meters per second. The 3 kilogram was moving at 1 meter per second. Don't forget to square those guys there. And what I see here, this is 1/2 of 1 times 9, so that's 4.5. This is 4.5 joules. 1/2 of 3 times 1, that turns out to be 1.5 joules. And I'm left with 6 joules. The energy afterwards is bigger than the energy before. This is an explosion. Because the energy that it had was stored inside that spring that I pushed together. That's where the energy came from. This is no different if I had fireworks or something like that, and I lit them off, and all of a sudden they blew up. At first, the firework would be just sitting at rest, and then later on, the firework would have some kinetic energy. The kinetic energy there came from the energy stored as chemical potential energy inside of the object. So this is the second part of this unit. In the first part, it was all about impulse, that the change momentum was equal to force times time. This one is all about conservation of momentum, that the momentum before and the momentum afterwards have to be the same. So if you stay organized with it, it's really easy. The number one mistake, again, the students make is to forget to put the signs in. And then you check afterwards and you see, is this going to be an inelastic, elastic, or an explosion, just by looking at the energy. If the energy goes down, it's inelastic. If it's the same, it's elastic. If it's greater than, then it has to be, if it's greater than afterwards, then it has to be an explosion. All right, everybody. Hopefully this helped. Feel free to email me with any questions, and stay organized, and hope everybody's being safe and healthy. All right, talk to you soon.